Yeah, recording has started. Sir, you please share your screen and please take forward. I don't know my availability. I might come in
Yes,
between
sir,
for a
yes.
few minutes. Yeah, please manage. Yeah.
Okay, sir. Yeah. So in the last session, I hope it is visible to all the screen.
Yes, the screen is visible.
Yes, sir. Yes, sir.
Yeah. So in the last session, you have discussed about this network architecture model, right? So in the entire network architecture model, you have discussed the two things. One, uh, context sharing and context migration. The whole story behind this entire model is the efficient sharing of instances, context instances, and efficient way of migration. This is the entire thing, right? As I said, in order to handle the real-time IoT applications, right? Neither this cross-vertical will help, nor this IoT fog node will help much. So on top of that, you require the two concepts. One is called as context sharing and context migration, right? So that we'll discuss in detail one by one. Exactly. Yeah. The model we focus, as I said, the model focus minimizing the service delay. The whole idea is to minimize the service delay, right? Because of the aforesaid network architecture without increasing the network and the fog node capabilities. So for that, what you have used? You have used this CVA, the cross vertical application. Uh, to handle the latency, you have used the node, I mean fog nodes, because if you go for a cloud directly, then the latency, overhead latency will increase. Then for massive data, we are using a cloud computing. Unavailability of types, right? This part I have not discussed the details, so we will discuss it. See, assume that in a particular fog node will receive a request of uh, smart weather information, right? So request to solve a smart weather information, right? So in that case, if that see, there may be different cases are there. One, the fog node itself does not have any application related to the request, or the fog node have the having the such kind of application, but required information is not there. Required information. See, for example, somebody will ask us, day after tomorrow, is there any strike in your area, right? As you have, as you heard from the national channels, there is a strike, all India strike. So, is there any effect in your area? How can I say that, right? The particular party is called throughout the nations, but whether that strike will affect in my area or not, I cannot say. So what I need to do, if I want to answer this, then I need to collect the information. I cannot simply say that by collecting a answer from one person. Just I'll go outside, I'll ask a person that whether there will be a strike in our area or not, or put the national strike will put an impact on our area or not. By asking one person, I cannot say, right? So if I want to give that answer to your questions, then I have to ask couple of students, couple of persons, right? So this couple of the number of, right, what I require the number of answers from the environment. So the how many number that depends upon the depends upon the context to context, right? If it is, for example, right, if I'll ask 10 members and 10 members will say definitely there is impact in our area, then I'll be sure that yeah, there will be impact on our, right? But in some other cases, right, right, for example, I will ask, is there any post office nearby? If one or two are say yes, then I no need to ask for many, right? So it depends upon the number of, right, it depends upon the request type and this particular point, the unavailability of type of context instances, right? For example, if a fog node receive a request, the request application is available in the fog node, but the required type of context are not there. So then we'll go for a smart context sharing algorithm, right? Just I will take an example. Assume that as I'm a teacher, for example, if one student will come to me and ask that, sir, can you solve this problem, right? Can you solve this problem? Yeah. If I know the subject, right, I can say yes, I can solve that problem. But to solve that problem, I need some other information. So that I will collect from others, right? This is one case. If I don't know that subject, then I cannot take that one because I don't know any. Even though I will get the additional information, but I don't know the subject. So how can I solve that one? So what I will do in that case, right, I will see the other person or other colleague who are good at that subject. I will simply migrate that problem to other one. So this is what you call as the migration, service migration, right? So critical IoT applications, the delay tolerant load balancer, right? These two we'll discuss in details. Yeah. So I'm switching to before. This is the first algorithm. This is the first algorithm that SCS, that smart context sharing algorithm, right? The first, just I block wise, I will explain this. I will get pointers or not. Okay. So this is the first here. The first section, right? We are setting the number of context information and minimum and all, right? From here. Then, so this is what you're taking. See, each sender. Okay, I'll go by one. At each sender site, right? In the environment, in the network environment, there are two types of users. One, the sender, another one is receiver. So the whole distributed algorithm is written in this form, the sender and the receivers. So at each sender site, right, what the fog nodes will do, they collect the information from the entire, they collect the entire neighbor information and keep in a table, right? And this is repeated with a duration of time period t, right? Then at each sender, each fog node do what you will do. This is randomly you are generating the maximum number of context instances for that one, right? And if that total context instances is less than that, then what you will do, the broadcast. For example, if I have 10 number of contest instances, but I required 20 instances to take the decision. So in that case, I will go for a broadcast that I explained in the diagram, right? Now this is at receiver end. What the receiver end will do, right? Check the availability of requesting context instances and send the number of context instances of, of requested type, right? So it will simply send. For example, I got a broadcast message from someone that I need this information. I will check that if that information is available with me, then I will send it. Now, what the sender will, once the sender will broadcast it, the sender will wait. Sender cannot wait for infinite of time, right? So it will wait for a small time period. Within the time period, if he'll get the number of context instances, based on the context instances, right, it will process and give the service to the request. Now, that is what the amount of time the sender has to wait. That depends upon the application type or the request type. For example, if it is a see the all request applications or all service requests, you have divided into three categories. One is high tolerable, delay tolerable one, and say medium. Second one is medium delay tolerable, and third one is critical. Means it cannot tolerate delay at all, For example, in case of medical and all, you cannot, I mean, you cannot, the system cannot tolerate any delay at all. So depending upon the delay, so this is the T. T is the delay tolerant for an applications. If it is a agriculture, then it can have right high tolerance. Means if the application can wait for a few seconds or few minutes also, right? Even if required, then few hours also it will wait, right? But if it is a right medical cases, then even seconds also is too critical. So here is the while T is less than the response time plus communication time. What we are doing that the response time as well as the communication time within the time period, right? You are allowing you are waiting to get the context instance from the other receivers. Once you get all these context instances, then we check that the total number of context instance plus NA, the number of context instances available, right, is greater than Cmax. For example, if I have 10 instances, I receive 20 instances. So altogether 30. If this 30 is greater than the what my capacity, if it is, then definitely the extra, here I'm calculating the extra number of context instances I need to migrate. I need to migrate to some other, or I need to keep this context instance in a near fog node, right? Nearby fog node. That is what you call as there is context migrations, right? So this is the delay tolerant load balancer. Here I'm called that this one. The delay tolerant load balancer is the second algorithm, right, which does this context migration. So overall, what I'm doing here, right, if the context instance types are available, right, then I will check that whether the minimum required context instances are available for to process the request or not. If available, right, then without broadcasting anything, I'll simply process the request and send the results back to the user. If it is not available, then I'll check how many are required. For example, for a particular application, I require 20 contest instances. So if I have only 10, then I will get another 10 from others nearby fog nodes by broadcasting a message, and they will share that, or they will share right those contest instances that they have. So while taking all these 10 plus those incoming context instances, I will process and give it. And that I need to do within the time period that the application supports the delay. If the application does not support the delay, then what I can do, then simply I can migrate the service request to some other. For example, like this way, if I'll get a request and the request context instance are not available with me, right? In that case, what I will do, I will first check that whether I can get these instances within the time delay what the application provides me. Means the application says that only this application can be delayed for 5 nanoseconds, right? So within that 5 nanoseconds, can I get those constant instances from the other and process it and give it the result back to the user? If no, then definitely I will not go for it. Simply I will migrate this service request to some other. So that is what you call as service migration. So there are three things are there. One is smart context sharing. Second one is context migration, and third one is service migration, right? So context migration, if the number of incoming requests, number of incoming context instances I cannot keep in the buffer, then the existing context instances I will migrate to some other fog node. That is what you call as context migration, right? This is what the delay tolerant load balancer algorithm, right? Exactly whatever I said, the context migration and this service migration. This entire steps deals with these 2 points. So I'm not going detailed step by step. It will take a lot of time. And here is reinforcement learning. So here I use you need a predictions, right? If a request allows me only 5 seconds or 6 seconds or 10 seconds, right, then I'm predicting that within that 6 seconds, can I able to get the required context instances from the other fog node? Can I and I can predict those. Sorry, I can process those within the time period. So that I am handling with the this is RL, reinforcement learning. This is a prediction approach that I use to predict this one. So you are moving to the PPT. Yeah. Service delay over percentage of information. This is the output. These are the outputs what you have got from our simulation model, right? This is service delay over percentage of incoming context instances with low Cmax value. Now, while you are simulating this one, right, you have simulated in a different range, right? Means you have changed the number of fog nodes, you have changed the Cmax value, right? You have taken the Cmax value in three types. One is low, medium, and high, right? With low Cmax value, how the system performs, means how the model performs. With high Cmax value, how the model performs, and with medium Cmax value, how the model performs. At the same time, you have also varied the number of fog nodes. Now here, the in this case, the number of fog nodes are static, I mean constant, and this is varying Cmax value. You have started the Cmax size of 500 to 8,000 also. Means you have 500 to you have changed to 8,000. An increment of 500 is right. As as the Cmax increases, Cmax means the total capacity, buffer capacity of a fog node. When the total buffer capacity increases, right, then the number of contest instances, contest sharing and contest migration will reduce. Once the contest migration and contest sharing will reduce, the total service delay also reduce. And once the buffer size reduces, definitely number of migration and number of sharings will increase. And this number of migration and number of sharings rate will increase the service time. Next, the service delay over percentage of incoming context instance with low Cmax value. Right. Here, uh, the number of fog nodes are fixed and the context Cmax is fixed. Now, what you are doing here, here the percentage of incoming instances, context instances, yeah, with low Cmax value. When the Cmax value is low, right, then you see that the service delay, when the percentage of incoming context instances very low, right, very low, in that case, the delay is almost, I mean, very low. The moment the incoming context instance increases, means you need to store the incoming context instances in your buffer. And if the buffer size is full or buffer size is not enough to accommodate the incoming context instances, then what you need to do, you need to go for a context migration approach. And the context migration approach will increase the delay. Right. Now this is same with a medium Cmax value. In case of medium Cmax value, the delay is reduced little bit because you are changing, you are increasing the Cmax value. And as you go on increase the Cmax value, the delay is go on reducing. And this our approach, the ECS approach, is compared with the greedy approach. Now this is service delay over percentage of migrated context instances, right? Now, if the number of migration will increase, then definitely service delay also increase, right? And this is what the first work you have discussed right now. And the extension, sorry. This is the second work we have published in the same IEEE IoT journal, IEEE IoT journal, right? A service delay minimization scheme for QoS constraint context aware unified IoT application. Now this is the same, just an increment version of the same paper or the same idea. Now here, what you have done, you completely focus on the service delay minimization, completely focus on, and QoS constraint means you try to reduce the number of service violations. Now, So instead of discussing everything, just I'll discuss only the additional parts here. Now, in this paper, yeah, this fog node can be a number of applications. All you have discussed in the first one, right? Now here, the fog node can process certain number of applications. See, what is the constant in that case? In the previous case, we are assuming that, or the entire model is assumed that one fog node can process one request, service request at a time. This is what the assumption is, and based on that, the simulation is simulated. The entire network is simulated. But as you know that there is a virtualization concept means from a single server you can create number of virtual machines. So and each virtual machine can serve one service request. The same concept is applied in case of fog node also, right? After this fog node is also a small computing device which can be virtualized, and each but one fog node can be virtualized into many virtual fog nodes, and each virtual fog node can serve a request. So fog node can process certain number of applications at a time. So one fog node process one service request at a time, whereas each fog node may receive number of requests of different applications. So first of all, at any point of time, a fog node may receive many applications or many service requests of different types also. So a virtualized multi-channel fog node architecture is introduced to process the multiple service requests of different types at a time. Now, what is the necessity of this one? Because in the previous architecture or in the previous model, a single node, a single fog node handles a single service request at a time, right? But nowadays, you know that each your desktop, your laptop, your servers can be virtualized, right? And you can create hundreds of virtual machines. The same way, a fog nodes can be virtualized, and a number of multiple virtual machines can be created in a fog nodes, and each virtual machine can capable of holding or handling the one service request. So a virtualized multi-channel fog node architecture is introduced to process the multiple service requests of different types at a time. It's not only same type. It means one virtual machine or one VM can handle that weather weather related information. Another, weather related service request. Another can be a transport related service request. Like this way, multiple virtual machines can handle the multiple types of service requests. So a multi-channel queuing model incorporated in order to serve the multiple requests at a time. Right. So fog node VM's storage capacity is not enough to hold the required number of context instances for all required applications at the same time. See, this is a constant here because when it comes to our desktop, laptop, or server, right, the storage is, the memory is huge in terms of GB. But in case of our fog node, the storage is very limited, right? So the storage at the buffer is virtually segregated to different virtual nodes, right? But this is something like your shared memory concept. This is something like shared memory concept, right? So an efficient context sharing within the virtualized node of a fog node and a migration approach is used to select the context instances to those who need to migrate to nearby fog nodes. Now, what is the benefit here or what is the advantage here? First of all, one fog node is virtualized to many virtual fog nodes, right? And each virtual machine can handle a service request. This is one. And the context instances which are stored in the buffer, right? The entire buffer is shared with the number of virtual machines. In that case, then the service, sorry, the context sharing within the fog node will reduce because actually you are not doing any context sharing within a single fog node, right? That is a shared memory that treated as a shared memory here. So that time period is reduced here. Then, in a smart multi-channel queuing model, all service requests are queued in a service request queue. So, in this particular model, whatever the service request comes to a fog node, it will keep all the service requests in a request queue, and the selection service request is based on the priority. Based on, for example, if 10 service requests comes at a time, then those service requests are processed based on the priority basis. Priority means based on the criticality, right? How critical that application is, whether I need to complete that application or the service request within no delay, then I will choose first that one. So based on the delay that can tolerate the service request, right? Based on that, the service requests are processed. A smart request scheduler is incorporated to schedule the incoming service request to virtual node depending upon the application and the number of context instances available with the virtual node. So before I schedule all this, right, there is a smart request scheduler, right? What the scheduler will do, right? It will first give a preference to the delay, how much delay that applications or the service request can tolerate, right? That is the first parameter. And the second parameter is, for example, one service request is on particular weather information. So it will check that whether the weather information is available or not, right? If weather information means the context instances are available related to that one or not. If available, then how many context instances are required to process the request and how many are available. If available is much more than the required, then simply it will schedule. If not, then it can put in the queue for more seconds, right? Then Cmax is the buffer size allocated to virtual nodes for a fog node. The total number of context instances of a fog node virtual machine can accommodate at a time. This you have already discussed in the first paper, right? Now here the contributions, the additional contributions here. If the number of context instances required for processing a particular application is not available at a virtual node, then it can collect the required context instances from other virtual nodes within the fog node. This is section 1 of algorithm 1. So that is service management algorithm. Means within a fog node, right? If in a particular virtual machine, right, the required context instances are not available, right? Then it will get it from the other virtual nodes within the same fog node. That is the first part of the service management algorithm 1. That's the section 1. In section 2, if the number of context instances are required for processing a particular application is not available within the fog node, means within all VMs, if context instances are not available, then it can collect the required context instances from nearby fog nodes within the minimum delay. That is the second part of the first algorithm, that is service management algorithm. Right. Then the third one, if computation and service delay can be if computation and service delay can be tolerated for a service request, but required context instances are not available, then the sufficient buffer size is also not available for the context sharing. Then the existing context instances are migrated to fog nodes, right? The selection of fog node is based on the communication delay, right? You see, here one more point is addressed here. If I have a 4 or 5 nearby fog nodes, right? If I want to migrate my instances to other fog nodes, right? Migrate in the sense, for the temporary purpose, I want to keep my context instances in other fog nodes, right? This is what the migration. So in that case, I need to choose a fog node such that, right, where the communication service delay is very minimum, right, which relies on the different parameters like nearby, less load, network traffic, and other. This you are dealing with this context migration algorithm too. Then, if the computation is not available, for example, the computations what you require for a service request, if that is not available, or The service delay cannot be tolerated for different reasons, right? The service delay cannot be tolerated due to computation or unavailability of application or unavailability of contest instances. Then the service request within service request with the application is migrated to other fog node, right? This is service migration algorithm 3. Now, to justify the efficacy of our model, again you have compared with the previous model as well as the greedy approach. Right? These are points almost are same, right? Now, this is what the architecture is. The system IoT architecture depicts the details layout of architecture, right? On top of the previous model, right? The first is fog node, the detailed fog node virtualization. The second level is the application layer, that is the domain application that a fog node virtual machine can handle. Then the third level is the context engine, right? The details of context instances and their sharing within the fog node VMs. And fourth one is context migration unit handles the context sharing, the context migration or service migration between the fog nodes. So this is what the context aware architecture, IoT architecture. On the top, you have fog nodes, right? Here, we are showing that this is fog layer, and this is the domain layer, and this is your context sharing layer, and this is context management unit layer. Now, try to understand this particular figure. This is one fog node, and this is another fog node. Just in this picture, you have taken the two fog nodes. Each fog node, right, there is a virtualization, that is VMware layer, right? On top of that, you have many virtual machines, 1, 2, 3, 4, like this way. So in each fog node, you can have many virtual machines, right? And as you have many virtual machines, then you can handle many applications at a time. So this is what you call as domain. Application 1, application 2, application 3, application 4, like this. So domain 1, 2, 4. For here, the domain 1, 2, 4 means you have given a short form of domain 1. For example, healthcare is domain 1. Then education is 2. Then smart health, waste management is 3, like this way. So each and every fog node maintains some domains, right? Like domain 1, 2, 4. In this case, 1 and 3. Right? It's not like all the domains are incorporated in one fog node, right? Now, on top of this, there is something called as context sharing, right? Now, see this one. There are two levels of context sharing here. One within the fog node, the context sharing. Another one is in between the fog node, the context sharing. Now, when it comes to the within the fog node context sharing, the delay is very less, or is the delay is negligible here. Now here there is one virtual machine, and this is another virtual machine, right? And this here the context engine A and context engine 1B, 1A and 1B, and this context instances need to access themselves. Means there is a context sharing. This required this context instance, and this one required this context instance. So this is, one VM, one virtual machines access the context instance of another one, right? This is what you call as context sharing within the fog node, right? Here the delay for the sharing is negligible. Whereas, right, in case of next, that context sharing level here, now this is one fog node and this is one fog node. The whole thing is one fog node, and this one is entire one fog node. Sorry. Yeah. This entire thing is one fog node, and this one is one fog node. Now, in such case, here, assume that if a service request requires some context instances which is not there inside the entire fog node, any of these DMs, then in that case, what it will do, it will try to get it from the nearby fog nodes. So that indicates this line, the context sharing, where some amount of delay right? You need to, I mean, some amount of time you need to waste. That is what is the delay, right? And on top of that, there is a contest management unit. Now, all these activities are under the control of contest management unit, right? This is what the contest aware IoT architecture. Then I'm moving to next, that is smart multi-channel queuing model with virtualized fog node, right? Now this is for the centralized fog server, right? This is for the centralized fog server. Now here you can see that this is a hardware event handler, right? And there is a database, there is MTTQ client and REST API capable of capability manager, virtualization abstraction plugin, then virtualization abstraction manager, internode orchestra, right? Now this is all, these are the all components within the one fog node, right? So on top of that, we are putting a hypervisor, right? And which will create the number of virtual machines. And on top of that, there is a fog node, fog API, right? Now, this entire this entire virtualized infrastructure look like this way. Means you have used a multi-channel queuing model. Now, what is this multi-channel queuing model is? This is the service request queue. Now, all the requests will come, it will store in this queue, right? And here is the smart request handler. Now, what is the role of this smart request handler? This will select the service request from the queue and schedule to a particular VM. And this smart request scheduler it contains the information, all the informations about both the queue as well as the virtual machines. Now, what type of information it holds? It holds the the computation, I mean, total resource capabilities of the virtual machine, and the context instances are available with the virtual machines, right? And the context instance available with the virtual machine. In addition that, it will check that what are the service requests are there in the queue. Now, it will pick the one service request based on the priority value. Now, here the priority or high priority value. Now, here the high priority is given to the critical applications. The, the applications which cannot tolerate any delay is called as critical applications or treated as a critical applications, right? So the application which cannot tolerate any delay, any additional delay apart from the computing, right? See, any service request has to compute, and for that there will be a computation time, right? So that is minimum. We cannot reduce that. On top of that, right? Waiting time means some service requests are like they cannot wait in the queue. So as long as that such type of requests come to the queue, the smart request scheduler will pick that one immediately, right, and sort to a virtual machine. Now, then there is something called as, I mean, apart from that, if the two or more critical service request arises in the queue, then those are solved as first come first serve basis. So why that scheduler is called as smart enough, because it takes care of all these parameters, right? Not only it takes care of the priority, but also takes care of this the availability of resources and availability of contest instances, right? So it's a multi-parameter, it's a multi-parameterized the scheduler. It's a multi-parameterized scheduler. It considers the multiple parameters and it's prioritize them, and if based on the prioritize, if the service request comes as a critical application, then immediately it will solve or immediately it will schedule, right? Now it says that if all VMs are busy with the some service is serving some service request, then immediately what it will do, it will ask this, right, this capability manager, right? Capability manager, it will send it to the capability manager, and the capability manager will immediately it will migrate to some other fog nodes. Because as I said, there is something called as service migration, because the service request is the critical one, and currently all these VMs within the fog nodes are doing computation with some existing task or existing service request. So it cannot be solved immediately. In that case, right, it will simply migrate it to some other fog nodes. That is what you call as service migration. Now, I'll come to the second point. If once the smart request scheduler finds that there is a critical service request in the queue, then it will pick that one and assign to a particular virtual machine. If only one virtual machine is available, then definitely it will assign to that, right? If multiple virtual machines are available, then it will find a suitable virtual machine for that particular request in terms of computation and in terms of the required context instance availability, right? Now here, while you are simulating this particular model, right, you have taken the uniform, I mean, all the virtual memory, all the fog virtual machines, right, a computation as a uniform, and in the second time, when you have taken as a non-uniform map. Just you want to see that how our proposed algorithm behaves if there is heterogeneous resources are there, because you are simulating, you are not going for a test bed. So you want to check that whether the proposed model will behave efficiently on the heterogeneous environment or not. So you have taken, means you have taken all this computation, virtual memory, virtual machine computation and storage capacity, right, as a heterogeneous, right? In both cases, the smart scheduler able to serve or able to serve, schedule the request to a suitable virtual machine which can compute and serve the request with minimum delay. And this what you have already discussed. So here I am discussing the entire model. In our model, we focus the minimize the service delay of aforesaid network architecture without increasing the network and fog node capability. The seamless integration of multiple vertical IoT application, that is CVA, to handle the latency you have used. See, in the previous case, you have used the only fog node to handle the latency. Now here you are using the virtualized fog node, right? For massive data, as usual, you are using the cloud computing for future processing. Unavailability of type of context instance, so context management algorithm, and the sub part is what the context sharing within the in between the VMs, right? The critical IoT applications with minimum service delay, the context migration algorithm or service migration algorithm. So there are three algorithms are there. The first one is context management, which deals with the context sharing within the one fog node and in between the fog nodes, right? And the second algorithm deals with the context migration, and the third algorithm deals with the service migration, right? Now this is what the results of the model what you have proposed, the performance of SMCQ model based on SMA algorithm with respect to CSS, I mean the previous model and the greedy approach, the effect of request arrival on total service time, right? Now this is what the in x-axis you are showing that service request arrival rate. Now here the subcarrier, you are using the subcarrier at 5 and service request arrival is 0.1, 0.2, right? You are taking in seconds. Now this is the total service time in milliseconds. Now as the service rate increases, right? Service request arrival increases, right? Then the total service time is also increases, right? And here total, this is the number of requests arrived at a time t. Now here you are taking the total number of requests arrived in a particular time t. You are taking this t is a particular time period. You are taking in case of seconds, right? In case of 5 seconds, how many service requests are arriving? If it is 50, if it is 100, if it is 150, 200, like this, right? You have tried to observe that if number of service requests are arrived, then how the service, how the model, proposed model behaves with respect to that. In that case also, SCS, sorry, SMCQ, right, smart multi-channel model, queuing model behaves much better than the previous one, and obviously the both are behaves much better than the greedy approach, right? Then effect of service deadline proximity on QS violations. Now, as I initially I pointed out, this model, right? Nor you are trying to reduce the number of, the service delay. You are also focused on the QS violation. How many service requests means in serving the service request, how many you have violated means how many this model is violated, right? Because that is the most critical part. As you can see nowadays, the service provider like the cloud service provider like Amazon, Google, and other, right? What they do, right? They used to complete. They used to complete your service request within the deadline, right? So that is what you call as quality of service violation, right? If they are unable to complete your service request within the deadline, what you call as QS violation, right? And nowadays the service providers are paying for that also. That means there is a penalty for that. If you violate the QS, then you have to pay the penalty. So those things are also taken care here, right? So we are trying to analyze that. Right? What is the QS violation rate here, right? See, the percentage of applications QA is violated. How much percentage is violated, right? Now, here the number of service requests with additional deadline, with a deadline of milliseconds, that is with subcarrier rate is subcarrier 4. Now we have here you have taken the 4 subcarriers and the deadline is fixed for 5 milliseconds or 10 milliseconds like this way. Now, here, when the service request is 100, right, 200, 300, like this way, you have, see, this is what service request with additional deadline in milliseconds. So, first we have taken as a deadline as 100 milliseconds, right? Then 200 milliseconds, 300 milliseconds, 400 milliseconds. Now, as you go on, increase the deadline, as you go on increase the deadline, service deadline, right, then the number of violations are decreasing. Number of violations are decreasing, right? Whereas in case of SMCQ and SCS model, the behavior of these two models are same. The behavior of these two models are same almost, but there is a slight increase in the efficiency in case of SMCQ, right? In case of SCS, right, if it is 100, the deadline, if you put 100 milliseconds, then around 4% of application service request applications are violated. Means this model is unable to process the 4% of service requests, right, within the deadline period. So then you're increasing to 200. When you're increasing to 200, then SCS is around 2.9 or 2.8 something, right? If you see that these two lines, that is the previous model and this model, the behavior is same, right? Because as I said, the network model, everything you have used the same, but what you have changed the multi-queue. Means you have used a virtual environment, right? And you have used a smart scheduler which smartly pick the right service request from the queue and serve it. That is the reason why the number of violations, QS violation is reduces. But the pattern is almost same. The pattern is almost same. The pattern is same due to the network architecture, because you are using the same network architecture, right? And the parameters what you have used, right? Those parameters also you are using the same. Then effect of subcarrier variations on QS. Now, in the last diagram, you have saw that the total number of subcarriers you have taken as 4. But here in this case, you have changing the carriers from 4 to 5, 5 to 6, 6 to 7, like this, right? So You have changed the number of subcarriers and you have tried to analyze the efficacy of our model. Right. This is the percentage of application QoS violated. Now, when the number of subcarriers are increasing, right, when the number of subcarriers are increasing, right, it slowly decreases the number of violations or percentage of violations, right? Now, all these three models like SES, Greedy, and SMCQ, the behavior of all these models are same, almost same, right? Because the moment you increase the number of subcarriers, right, then the service rate will increase. When the service rate will increase, then the number of QS will decrease. So the behavior is almost same, but whereas SMCQ model, it outperforms, right, over those two models. But you can see, if you ask that what is the best, what is the best now? I mean, what is the best case for number of subcarriers? Here you can see around 4, 5 is the best, because the moment you reduce less than 5, then suddenly there is an increase, right? And after that, there is a slight decline in the percentage. But this is a simulated environment. But in real case, it's little, I mean, very deep. We don't have much flexibility to change the number of subcarriers every time. So that's why these simulations will help us to, right, design the real deployment models. Now, this is the variation of total service time with varying the number of fog nodes. Now, here what you have done, you have changed the number of fog nodes, because as I said, the number of fog nodes you have taken in the environment, right? You have changed the number of fog nodes, right, and try to measure the efficacy. First, we have taken the 30, 35, 40, 45. Just simply you are changing, varying, I mean, increasing by 5, 5, 5 each time, right? Now, some can question that why you are taking 30, 40 these numbers, two-digit number, why not more? You can take the more numbers, no issue, but the problem is you require some high-end systems to compute this, because as you increase the number of fog nodes, then each fog node's configuration you have to set, right? And each fog node has its own queue, a multi-queue, and number of virtual machines, right? So that is the reason why you have restricted the number of fog nodes within double digit. And here the total service time in milliseconds, it's something like reducing. Now here, in this case, the SCS and SMCQ, there is a slight difference between these two models, right? There is a slight difference in these two models when the number of fog nodes are less. And as long as you go on increase the number of fog nodes, the difference is little bit. I mean, the difference between these two models are increases. And here also this SMCQ, right, model outperforms the other two models. Right. This is effect of varying uh, request arrived in an interval of QoS violation. Right. Now here the number of service requests arrived at time t. Now we are trying to see the, right, how much, I mean, the QoS violation, whether it depends upon the arrival rate or not, right? Arrival rate or not. In a particular time period, if 50, now here, let me give the information here. In this case, the number of fog nodes are fixed and soft carriers also fixed, right? But every time, right, the Cmax will change, because Cmax you have taken a random, and applications will also change. The number of applications, right? As I said, you have taken around 13 applications, right? Different type of application like smart healthcare, smart education, smart transportation, like this. With 13 you have taken, right? And each and every fog node contains around 7 to 9. It's a random value within the 7 to 9. Some cases 7, 8, some cases 8, some cases 9. So these parameters will change for each and every time, right? So those are the random parameters that will change each and every time. Now, what is constant here? Here the constant is the um, number of subcarriers you have used, that is constant, and number of fog nodes are constant. So with respect to these two, you're trying to analyze how the model performs here. So in that case, when the number of requests for a particular time period is 50 or less than 50, even less than 100, right? Less than 100, yeah, SMCQ is the service violation is zero. I mean, the efficacy is 100%. There is no service violation percentage at all. QS violation percentage at all. Right? Even in case of SCS is also not there. Only in case of this greedy approach. Only in case of greedy approach, and that is also something 0.1 or 2. Right? But as the number of service requests, right, increases for a particular duration of time, then you can see the number of violations are increasing, right? Particularly in case of 500, right? Now here the time you have taken for the 10 seconds, right? Within 10 seconds, if within 10 seconds, the this this is also changed. I mean, the time period is also changed. 5 seconds, then 7 seconds, 6, 7, 10, like this we have varied that. But this particular figure of the out result you have taken for particular t value. Now in that case, now when the t is in, sorry, the number of requests are increasing for a particular time period t, then service violations also increasing. Now here you can see that in the previous two models, right, the SMCQ and SCS are almost same. I mean, there is a slight difference, but when it comes to the number of requests, when it comes to the number of requests within a particular time period, right, there is a huge difference between the efficacy of these two models, the previous model and this model. The reason is we need to analyze in this way. In the previous cases, right? In the previous cases, what you are measuring, right, that does not impact on the number of virtual machines in a particular node, right? But here, as the number of service requests are increasing, right? So definitely that put an impact on the number of virtual machines in that node. Previously, in the previous model, you have not taken any virtual machines at all. One node means one machines. But here, one node means number of virtual machines, right? So as the number of virtual machines increases, then the service violation decreases in case of SMCQ, right? That you need to observe here. So even 500, even the 500, see, in case of even 500 requests within the time period t, right, the QS violation is very less, around 0.8 or less than that, right? But you see the SCS is something like SCS is something like close to 3.5 or more than that, right? That is the difference that what we observed here, right? We observed here that if the number of virtual machines is increased within a fog node, then definitely there is a reduce in the service violation. That is a good sign of this particular model, that if we can virtualize if you can virtualize the fog node, and if you can create the more number of fog virtual machines within a fog node, then the QoS violation completely reduced, maybe 0 or less than 1, right? So this is what the model that the two papers published, right? And the overall idea is to use the concept of fog nodes, use the concept of contest aware, and with these two, the suitable approach to handle this. That is, either you say a smart contest sharing, right? Smart contest migration or service migration. So, I mean, out of this, I can conclude that neither for a real-time applications, for a real-time critical IoT applications, right? Obviously, for cloud computing is not as suitable at all, right? So people can go for a fog computing, right? Or people can have a fog node as middle layer, But only a fog node cannot be a solution for that, as the number of requests are increasing day by day, exponentially increasing nowadays, right? So with that, you have used or you have incorporated the concept of contest saver. Along with that, the smart contest sharing as well as contest migration approach. So that is the overall idea of using this one and our achievements. If you have any questions, then we'll happy to answer those.
Huh. Yes, sir. Done. Hello, am I audible?
Yes, sir, you are audible.
Okay, okay. What
Yes, sir. Yes, sir. Audible. Yeah.
So we'll take questions.
Sir,
If there are any questions from this session.
yes, sir.
I hope you have covered, sir.
Yeah, two models I have discussed, right?
Okay.
And the difference between two models I have discussed.
Okay.
Right.
I don't think we have
within
sufficient
a short
time.
period of time.
Yeah, we have to stop in 10 minutes anyway for the validity. So we'll just like to have any, not just questions from technical, if you could, for that matter, just any discussion would be greatly appreciated. We are welcome to do that. We'll just wait for 2 minutes. If there are none, of course, then we have to stop.
Okay, sir.
Something is there in the chat box, I guess.
Yeah, even if any technical questions also, no issue, can happen.
Yeah, so anything will be welcome. There is a lot, I think participants are more active in the WhatsApp group to settle down the schedule for the exam, end of training exam, which isn't such a big issue. So in that case,
within a short period of time, it's difficult to digest the two concepts.
No, that is okay. So we are ready to discuss further. If anybody is interested, we actually we are looking for collaboration. So anybody, any ideas, we can
It's an idea only.
Yeah, we can detail it out if you come with our idea, and we can further collaboratively we can do, both parties win. So I think there are no questions, no point in pondering on it again and again. So with that, with this, what we do, we'll stop. May I please stop the recording then?
Okay, sir.
Yeah. So good. At least one session should be a bit short.